Hi, it's Bruce, and welcome once again to my Rocky Mountain Lab. As today we're going to take a look at a very nice Tektronix 465 oscilloscope. These scopes debuted about 1973, and I think they produced them up until about 82. They had a good long run. Probably the most popular scope they ever made. There were actually multiple versions of the scope that came out. There was a 465M, a militarized version that primarily was used by the Air Force, and uh, it was modularized but very similar circuit-wise. Uh, the shielding that they used on the 65M is different and so on, but uh, like I said, it was probably their most popular scope. At the time, it sold for, I don't know, just under $2,000, and at that time that was equivalent to about $10,000. So pretty serious investment in a scope. This was not a low-end scope. It was a very decent high-end scope, but it performed really well. And as you're going to see, this one does too. It does a beautiful job. All right, well, let's just start by kind of taking a quick physical tour of the unit. First of all, here's our faceplate, very clean, no scratches, no damages that you can see. That's little bit of wear and tear on the word auto here, for instance. Nothing big. Everything looks very nice. Bezels in nice looking shape. Cabinets in decent shape. We got a little mar here or there that's, it's going to get knocked around over 40 years, so you're going to get a little ding or chip here and there. But all in all, beautiful. I've also given it. Disconnect this. I've given it a couple of feet. The old feet were destroyed, really bad shape. This one's even worse. So I replaced them. They are not matching feet, but yet the cord wrap will work good, and it'll be a good stand. So handles in good shape. Cabinets in good shape. We've got some good feet on the bottom. See if I can hold this thing up here. It does have some weight. See the feet there. All in all, excellent shape. So we're going to go ahead and take it through some of its paces. Hang on, we'll do it. I am going to shut my blinds here. We've got way too much light coming in for this camera to be seeing the traces good. All right. Well, to begin with, we've got an extremely nice, crisp, bright trace on this thing. We can take the brightness from completely off to just visible to extremely bright, and then back down again. So we've got a lot of brightness. A lot of that's got to do with the power supply and the tunnel diodes and so on that are used in the circuit here. We are looking at a 10 megahertz signal right now, and that signal's coming in both channels A and B. We've got them overlapped, as we can see here. If we separate, moving channel 1 vertically or back down again. So we mate them so you can't tell they're there. And We do this because we want to demonstrate that the thing is in good calibration. We're putting in a 5 volt 10 megahertz signal, and right now we're on 1 volt per division, so we're going up 2.5 and going down 2.5, and that's on both channel 1 and 2. And they overlay, and you can't tell that it's more than one trace. If I change channel 1 to 2 volts per division, so we've divided by 2, then you begin to, of course, see the difference. 5 volts per division, there's one division. And then if I do the same thing to match it on channel 2, I'm going to touch up the trigger. There we go. Again, we see that they're matching. Let's cut that voltage down. Okay, here we're going 1 volt per division. So we've got up 1, down, excuse me, we're on 0.5 volts per division. So we're up 1, down 1, that would be 1 volt. 0.2 volts per division on channel 2, and on channel 1 and channel 2. And we see ourselves going up 2.5 and down 2.5. That would be a total of 5, which times 2 would be 1 volt. 0.5 times 2 is 1 volt. And let's take her down again. Leave ourselves. All right, we are at 0.1 volts per division. Here's 50 millivolts per division, both channels. 20 millivolts per division, both channels. 10 millivolts per division, both channels. We got to cut down our voltage again. All right, now we're reading 0.04 volts or 40 millivolts. And so we go up 2, down 2, that's 4 divisions times 10 millivolts per division, 40 millivolts. And then 5 millivolts per division. We're going up 4, down 4, that's 8. 8 divisions, and we are 5 millivolts per division. That'd be 40 millivolts, and we are putting 40 in. So, and we see that we still are overlapping beautifully. So the vertical traces on this are working very, very nicely. They're calibrated nicely. Let's take a look at one other thing. Cut this down a little bit. We'll invert channel 2. And, okay. So now we see the diamond necklace because we've got 2 sine waves. They're 180 out of phase here. Anyway, if I add these, then we get the straight line. And that's as we should, because if they were out of phase with each other, as one goes up, the other goes down, the net effect is 0. So take the invert off, and if we add the 2 signals together, we double them since they are now in phase. And if I go back to alternating, we should see half. There we go. All right, so now let's take a look at the horizontal. Now this thing has 2 horizontal time bases, which is a good thing. You've got the standard time base A, which you'll use every day. And then you've got a second time base with a time delay involved on B. And the idea is you can use the second time base and time delay to zero in on any portion of a signal on the screen and then magnify it so that you can see more detail without leaving the position that you're on and disturbing the first few cycles that you decide to let through. Now let's see, if we want times 10 magnification, push in a button for times 10 and we expand the horizontal signal, no problem there. If I just turn up the frequency, well, we're all the way up on the end here right now, so it's almost a 100 megahertz signal. Okay, so right now we're looking at the 1 megahertz normal sweep signal. Let's turn it down a little bit. Okay, and we'll turn the brightness up just a hair. Okay, so we're looking at the main sweep. We are going to input 10 megahertz into here. And I'm going to, after 1, 2, 3, 4, after the fourth cycle of the waveform, I want to see what is in the middle here expanded. I want to get a closer look at it. Well, I can do that because of the second time base that's on this unit. So right now we are looking at the main time base, so just straight time. Let's go ahead and you see this highlighted portion here. You can't miss it really. 1, 2, 3, 4. I want to move that highlighted portion by moving this time delay knob up here to the fourth cycle. So let's see. Right about there. So after the fourth cycle, I want to expand that region. Well, I can now punch in the mixed button, which lets me look at the original time base and then the new time base, which is a little bit faster. And I see 1, 2, 3, 4, and then all of a sudden I see expanded, the portion of the wave. Now I can change the amount of expansion, make it more, make it less. But it will always be a little more expanded than the normal wave. And if I just want to take a look at the expanded waveform, then I can hit B delayed, and that'll show me only the expanded portion of the waveform. So here's the area I'm looking at that's B intensified. Mixed gives me the original, then after the time delay takes off with the expanded waveform, and then back to the normal. So that's the time delay portion of the unit and what it does for you. Right now we're triggering in auto, and when you're in auto, if you're not triggering on this, you're going to see the original untriggered display, but it's all fuzzy. You see the band, you know that the signal's in there, and then when you do finally start to trigger on it, you'll see it lock in. Plus you'll see this light up here, light to tell me that I'm locked in. And if you're in normal, when you're in lock, you can see something. If you're not in lock, you don't see anything. So you don't want to be in normal when you're first coming in to look at a display, because you'll be all confused. At least I am. So I like to be able to see my signal. I usually run myself in auto like that. I can trigger on channel 1. We're displaying channel 1 right now. If I was to display channel 2 in auto, I don't have a signal going to 2 at the moment, but we can put one on there. And we can put one on 1 as well. Doing that. Well, if I don't have a channel 1 signal right now, because I'm triggering on channel 1, I don't have any lock. If I move myself with this switch here to channel 2 and adjust my lock, there it is. So I'm locked in on 2. If I go to 1, I have no display at the moment. Okay. That takes care of that. I also have a line and an external sweep where I can feed a signal in to trigger. This would be my internal, and it's my external signal in. I have a calibrator here. We should take a look at that, but I'll have to switch to my probes to do it. Here's my horizontal positioning control and the fine control for that. Okay, so now we're going to take a look at the calibration test point, and to do that we're going to use our probe. And when you're trying to adjust the capacitance of the probe, you want to be in the times 10 position. This is the high impedance position, and it, in conjunction with the capacitance of the probe, makes it a lot more significant. The adjustment is a lot more significant. Let me give you an example here. Right now we're actually properly adjusted, but we're going to misadjust ourselves here on purpose. Within the inside of my probe, I have a little hole here. Sometimes it's on the bottom end of the probe, sometimes it's in the probe handle itself. This one's in the handle. And okay, I'm in it. So now you can see that my square wave is pointing down. That's undercompensated. There we go. This is undercompensated. Square, the most square is where you want to be, and this is overcompensated. So I'm adjusting the capacitance to give me the best square wave. And I'd say that's pretty much it right there. Okay. Now we also are in the 20 millivolt per division position right now. Now if I went to the 5 millivolt per division, I got 1, 2, 3, 4, 5, 6 times 5 would be 30 millivolts peak to peak, and I'm supposed to have 300 millivolts, but then again I've divided by 10, so 300 divided by 10 would be 30. So the 30 millivolts is correct in this position. Now if I put my probe back up, make sure we're zeroed, and then I put my probe into the times 1 position, 50 millivolts per division. Let's go 50. We were at 5 earlier. So here we are, 3 up, 3 down, that's 6. So 6 times 50 millivolts is 300 millivolts. So we've got a 300 millivolt peak-to-peak square wave. And that's what we wanted. So the calibrator is working fine, and that's basically how you'd use it with the probe. So here's a couple of other things I just want to point out. There's no knob on it. It's done with a screwdriver, but there's an adjustment here for astigmatism. And what that does is it sharpens the trace by, say when you put a point on here, instead of, well, let's show you. There's a point. And what you do with that astigmatism is you adjust that point for the best roundness. Otherwise, if you got a little, it could look like a small line or a dash. That's not adjusted right. When you've got it round, that's right. That's going to give you the best trace. Then the other thing you have here is trace rotation. And you use that, like right now our trace is perfectly flat. But let's say that the trace veered off on the right end and it actually rose above the line. Well, that's because that trace needs to be rotated slightly one way or the other. In order to counteract that trace going this way, you rotate the control so you lower it. And that's what the trace rotation does. You make it so you get the most even line there, when you're not feeding a signal in, and that's going to make sure that you have a good trace. But that's a feature that's nice to have handy right there on the front. So that pretty well does it. We can go ahead and power this down. Here's the power button. And this beautiful scope will be up for bids. Happy bidding to everybody who does so. Along with it, I will be providing on a CD the user and the service manuals and the schematic diagrams that go along with this scope. So you have all the information you need to learn how to work with it. You'll have your service documentation for maintaining it, and you'll have your schematic diagrams for, hopefully you never need them, but any possible future problems. So you'll need to provide yourself a set of 100 megahertz probes, but I think you'll be able to find those for between $10 and $15 a pair on eBay. So thank you for watching, and happy bidding, huh? We'll see you next time.